Hey, my name is Michael.
I'm Charles, and I'm your narrator. This is an inelastic collision. Michael and the board stick together as one, so they must slow down. This is the first diagram for the collision. Now this is how it's done, the equation. Now the equation for it is mass 1 times velocity 1 final plus mass 1 times velocity 1 initial equals negative mass 2 velocity 2 final plus negative mass 2 velocity 2 final or initial, whichever one I said. Now, because we don't know how fast Michael and the bird travel afterwards, we are solving for the final speed of when they're combined. And that's how that's done. Now let's look at an elastic collision. As you just saw, that was an elastic collision, and here's the first diagram. This is the equation for an elastic collision. It is mass 1 times velocity 1 final plus mass 1 times velocity 1 initial equals negative mass 2 velocity 2 final plus mass 2 velocity 2 initial. Now, in this equation, we are solving for velocity 2 final. So let's solve. And that's how this equation is done. Now remember, since we rounded off, there is some human error, so it is close enough for practical standpoints. Now, again, on the very first scene, there was physics. Let's relook at that. See, Michael has potential energy now, which is being converted into kinetic. Let's look at that, because that is actually a crucial part of physics. This is the diagram of Michael on the hill. Now, to solve for how far he travels, we must look and use Pythagorean theorem. He started off 20 meters high, and the hill he travels is 40 meters, but the actual path he takes is not 40 meters, so we have to use Pythagorean theorem to solve for it. Now, Michael starts at the top of the hill, so he has potential gravitational energy, or MGH. And that, while he's moving, is going to be converted into kinetic energy, while some of it's dissipated to sound and heat. Now, the kinetic energy formula is 1/2 mass times velocity squared. But what you're seeing right now is an energy diagram showing how the potential gravitational energy is all going to be converted into kinetic. At the moment, we are not adding in energy dissipated, but we will add it in later.
392 equals d squared.
Now, again, you've just seen how this problem's worked out, and we're coming to the final kinetic energy. But as you can see, it's not equal to the gravitational energy because there's energy dissipated. So to solve for the percent of energy that is dissipated, you use potential energy, gravitational energy over kinetic, and in this case, we solved it for 9.39.
9.39% of energy. So that was our physics project. Hope you enjoyed it. Peace out, Renan.
And I was your narrator, Charles Johnson. I hope you enjoyed it.